by me. So here's me sharing my screen. Tell me if you do not see my screen. So I will start by thanking everyone for having attended this workshop. Never mind attended this workshop, for having sort of hung out with me over the summer. Never mind hung out with me over the summer for the last several years or so. You have no idea how thankful I am for it. I'm also thankful for yesterday's company, which may have phased into today's slides somewhat. Before I move on to the next slide, I will present an apology. If what follows is boring to you, is of no interest to you, I assure you that genuine work has gone into preparation of these materials. Ironically, the people who will benefit most from this material are otherwise taken, so their lives are busy right now with other things. And so just as a reminder, I presented several several equations that describe our biological systems. Furthermore, Dr. Goldman has just finished describing even more physics on how we describe the biology of the hemodynamics, of how stuff moves from here to there and everywhere else. Yeah. And so now I thought we should get closer to the bone and find out about how numerical methods look like that are used to solve these equations. So some of us use ImageJ Fiji, some of us use Chaste, Randa uses VCPL, I use Chaste, most of us use SimVascular in one way or another. And all of them provide you with numerical solutions, because analytical solutions of these PDEs are not sort of possible. And if they are possible, the clinicians cannot really benefit from the simplified analytical solutions. So this part of the session, this last part of this year's workshop, is about numerical methods that we use, and I'll use a few equations as examples to illustrate how the numerical methods work. And so before we move on the left-hand side is how it was a few years ago. And on the right-hand side is how it's going now. And so you can see that I had a striped shirt, a brown belt in 2016. There was this cheeky young man hanging out with me. Next to him is Andrea Casse, who's now in Saskatchewan. She's training to be ICU doctor. And right next to her is a very intelligent, clever young woman called Kiera McDougall. It is my misfortune that Kiera decides to go and do something else. As I understand, she's now making lots and lots of money in a very high-powered management job. I'll appease myself by saying that she does not enjoy her job at all. There's another picture on the left-hand side bottom, where again there are two common components over there. The cheeky young man with his grin, and me with my stripy shirt, brown belt, and dark trousers. You can also see someone in a red shirt, and that is our Karavi Desai, who has now abandoned us to go and study medicine in McMaster. The bottom left-hand side picture was taken a couple of years ago, 2-3 years ago. In contrast, the picture on the right-hand side, where I have my striped shirt, brown belt, and dark trousers. I refuse to go shopping. I hate shopping. I hate everything. But that picture was taken yesterday, and those are that's some of our fresh blood. We have in a clockwise manner, starting with me. We have the young Yusuf, then you have Tim, followed by Daniel, and next to Daniel, on Daniel's left-hand side, is Sadie J. So there we have fresh blood over here. So that's how it's going now. And so I wish we were joined by many other people. There were at least 2 other people who are not in the photograph. And for that, I don't know, they're just not in the photograph. So that was sort of a little bit of a digression. Moving on, I put this slide here because for two purposes. Firstly, because perhaps Dr. Frisby, if he was here, would have appreciated it. And Keith and me, we were talking about exactly this yesterday, in that we are making all these models, both mechanistic and statistical. And so our aim is to improve the lives of critically ill patients. Yeah, fine, okay. So Keith asks, how are you going to do it? And so the arrows might guide us towards how we might do it. And the overall summary, the message of this slide, people, is that everything in the blue boxes, in the yellow boxes, the models, the validation, which is essentially estimation of your parameters, model identification, and the word for validation, the verification, to reproduce known knowledge and to generate experimentally verifiable hypothesis, verification. All of these have to come up to standards that have been agreed by not you and me. There are certain persons in authority inside of, say, for example, the Food and Drug Authority, the EU Health Agency, and other agencies such as the American Society of Mechanical Engineers. They all prescribe standards, and we have to comply with those standards prior to our models being useful for saving critically ill patients' lives. And so the pipeline might go as take your model, make sure it is validated, make sure it is verified, do a whole bunch of sensitivity analysis just to convince yourselves that the model is sufficient, not too little, but not too much either. And then to be able to convince the clinician on how much they can actually rely on your modeling results. I propose that we push it through a extremely refined platform shown on the right-hand side top called Uncertain Psi. This is a brand new platform, Python-based platform, that has just come out of Utah Scientific Computing Center, specifically through a friend of mine, Frank Sachse, a senior friend of mine, Frank Sachse. And we will be uptaking this platform, Uncertain Psi, for Tim's upcoming work, for Clara's upcoming work, definitely for Lawrence's upcoming work, because this is a platform that is firstly extremely elegant, is based on robust mathematical and biophysical principles, and importantly, it is compliant with the FDA and other agencies. Of course, our reports that we generate over the next 2 years as recommendations for the experimentalist and the clinician may not be the end results of the process is not linear. Rather, I believe that it is cyclical in that our reports may generate other questions, other refinements, which then has to go back along the red arrow and feed back into your model making, validation, verification, and again, compliance testing. So making sure that everything that you do is compliant with people who decide what is compliant and not compliant. One of the reasons why people use software such as ANSYS and not the SimVascular open source software is because they need for their results to be compliant for a process similar to this cyclical process that I've shown here. So Keith, I hope this addresses some of your concerns. And you may appreciate that at each arrow and inside each of these boxes is a long list of hurdles that you are going to help us overcome. And so this is roughly about how things are going to go. Even before I start, once again, shown here is a very recent publication that I saw that illustrates the dual cardiotoxicity of cancer drugs. And the cancer drug in question over here on this slide is called doxorubicin. And so on the left-hand side, the histology shows you that there is genesis of fibrosis. So Randa can go take these histological sections and show that there is a propensity of a certain kind of arrhythmia in these hearts. On the other hand, on the right-hand side, we can take Dr. Goldman's large number of equations and show that the consequences of the loss of endothelial cells, especially in the top row on the right-hand side, that says cardiac EC. So there's definitely a difference between the images for no docs and docs, no cancer treatment and cancer treatment. And apparently there is less endothelial cell function on the right-hand side when you've given 1 micromole of dox treatment. So you might be saved from the cancer, but you might suffer from, say, for example, heart failure, is what this publication is saying. So oncological drugs have significant toxicity. So moving on. This is my first recommendation to everyone. There are 2 classical books that I thoroughly sort of suggest to everyone, especially Tim and Jeremiah and everyone in between. The blue book, the cover with the blue book, is Numerical Recipes designed for Fortran. I believe it is not just for Fortran 77. You will find all kinds of algorithms for Fortran 90 as well. There's been recently a generalization of Fortran called G-Fortran. And G-Fortran may or may not be able to handle all kinds of Fortran, as well as speak to other compilers. And this book is sort of the book for numerical recipes. There's not much that is not in this book. And if, say, for example, you program, say, in C, there is a book for that too by the same authors. It's sort of proposed to be, and it is teaching you the art of scientific computing. And it says it gives you numerical recipes in C. I regularly use numerical recipes in C. This book is obtained both in print, and the latest variant is, I believe, available from our Western libraries in electronic form. If anyone is interested, there is a link at the bottom of this slide for numerical recipes in C. Numerical recipes in Fortran was developed by the National Algorithms Group, who have recently moved from Edinburgh to Oxford. So the blue book is made by the NAG libraries. But fine, so that is a very strong suggestion. And the first piece of numerical methods that I'm concerned with is about parameter estimation, is to find the functions f that we discussed a couple of days ago. And so for this, I would suggest that there are 2 ways of going about estimating parameters in your known functions. So the problem is that you know f, rather you know how to do a simulation. If you are given a set of modeling parameters and you want to identify these parameters based on experimental data. And so to do so, on the left-hand side is a very brief, terse summary of a method I used many years ago, application of which we may or may not see in a minute. And that could be called the steepest gradient method, which says that your estimated or identified parameters, Pn plus 1, are essentially the parameters that you have guessed or worked out at the last iteration, subtracted by the slope of the difference of your simulation and experiment. So that is what makes it the descent method. It's also called the gradient method, okay? So this is the long and short of the steepest descent method. If you took just the gradient of the cost function, you would be moving really fast. And so you have to use a small number to control your progress. So you have to invest some time and patience in arriving at a reasonable identification of your parameters that gives you your simulation close to your experiment. That was the steepest gradient. But as Jay has decided, they are just going to keep guessing millions and zillions of combinations of these parameters, keep solving your system, and then you use your guesses in your system and find out if your particular guess takes you anywhere acceptably close to the solution that you're looking for. And whenever that happens, that is an acceptable solution. So this is a bucket load of redundant work, but from a programmer point of view, this is very straightforward to implement as soon as you have a system given. Now, I would like to draw everyone's attention to peculiarities of most biological systems as illustrated in the diagram over here. And so I have two parameters on the X and Y axis. There is a parameter that goes between minus 0.5 and 1 called A. And then there is another parameter B that goes between minus 1 and 1. And using this A and B, I can then work out my simulation, my result, whatever the X may be. It's my simulation, so some pressure maybe, some sort of cardiac electrical potential maybe. And if I then compare that to experiments, I get a surface like this. So if I subtract my simulation from my experimental data, I get a surface something like this. And that surface is called the cost function. The aim of both the steepest descent and simulated annealing is to get to the global minimum of this cost function surface. But supposing by some horrible luck, you start your initial guesses in one of these troughs, you can see that your method may struggle to get over these troughs, especially if these troughs are many. So you might then ask, how many such troughs would you expect in a typical cost function? Unfortunately, we have infinitely many such troughs. You might then ask, is there any way of prudently guessing your initial values of your parameters so that you can arrive at the global estimate of your parameters properly? Unfortunately, I don't have a very straightforward method. Okay, but these are the two methods that I would like to we will be using for the near future. So that's how you might do parameter estimation using the methods that we have. That's fine. And so how were these methods successful ever? And so shown here is a result that was generated a few years ago. Sorry, I have to pause for half a second. Okay, so this was a result generated a few years ago. Yeah. And this is me describing or trying to describe mouse sinoatrial node cardiomyocyte electrophysiology. So disregard the right-hand side panels. Let's just focus on A, B, and C over here, where panel A is the experimentalist's recording. They isolate one cardiomyocyte from the mouse's sinoatrial node, and they make an electrical recording. And they have about 5 excitations or 6 excitations in about 1.5 seconds. In contrast, there is a guy called Matteo Mangoni, a very accomplished experimentalist, and he studies the L-type calcium channel current in the mouse in the sinoatrial node. And so back in 2010, 2011, he had just obtained his brand new fresh measurements of steady states and time constants for these specific cardiomyocytes, and notice how, and then he went and tried to generate the action potential for the mouse sinoatrial node. You can appreciate that there is a significant difference between what is shown in the experimental recording and Mangoni's mathematical model. So the morphologies of these electrical excitations are not necessarily the same. They are far from similar even, never mind same. On the other hand, after yours truly used the steepest gradient method, some Greece and lots of time, you can see that at least the shape of these spikes start to look different. The other thing that was also optimized that is not clear in a diagram is the upstroke velocity of the experimental recording. Fortunately, I could definitely match the model's ability to produce that upstroke velocity. Furthermore, there is a value, Randa, called the takeoff potential for these oscillators, after which they are in an excited state. And the takeoff potential for the experimental recording is pretty close to what the 2011 model says. Okay, and so an application of the parameter estimation methods that are available to you people: steepest gradient and simulated annealing, in addition to Nelda-Mead. But fine. So moving on from parameter estimation, here's a couple of diagrams. On the left-hand side is a photograph I made in the Institute of Engineers that is located in the city of Westminster on a street called the Strand in London. So the statue is of Michael Faraday, and there's Michael Faraday looking really clever. And following from yesterday's discussions over dinner, on the right-hand side is shown a mural from Charing Cross Tube Station, where there's lots of people working hard. For what reason, I do not know. And there's a few other people who are not working so hard either. So that's Charing Cross. Very close to this mural is a hospital called Charing Cross Hospital, a very traditional hospital in that it was one of the first National Health Service hospitals. And that is where our Dr. Christopher McIntyre trained for his medical training. Charing Cross everywhere, with lots of informative murals. But fine. So moving towards actual numerical methods for solving differential equations, I would like for everyone to take note of the first thing. And this first thing is something called a Taylor series of a function. So this curly f, this italics f, is a function that you know. You know this function at time t0. At some value of the independent variable, you know this function. And for some odd reason, if you need to work out this function at time t0 plus a small time, okay? So t0 plus dt is a very small time, okay? So if, say, for some reason you had to work out the function f at time t0 plus dt, then Taylor's theorem comes to our rescue and tells us that you take the value of the known function f at t0 that is known to you, and to that you add a derivative of that function evaluated at that time t0, and then there are some multipliers and divisors. Okay, so there's a first order term there, and then if you're not satisfied, you then add another term to that, which is a second derivative of the function. Yeah, there's a divisor there, and then there's a multiplier of the small time dt. Yeah, dt is some 0.01 or something like that. Yeah, and you keep going with that till you're satisfied. So what is satisfaction? We might come to that in a minute. Okay, and so the conditions for Taylor's theorem, Taylor series, to be valid for a small number of terms. You know, you don't want to be working out an infinite number of terms. You just cannot. You have to stop at, say, 1 term or 2 terms or 3 terms or maybe 4 or 5 terms. And the condition for that is that as long as you take your dt to be small, then a few terms on the right-hand side of the equal to sign, so a few terms are sufficient to give us an approximation of the left-hand side of this thing here. Okay, so this is relevant in numerical methods. This is one of the relevant parts. This is the smallest relevant part of things. Okay, but this is Taylor's theorem, people. Okay, and so I've tried to caricature how it works in the figure on the right hand side. So if, say, for example, your f is going according to the red line, and you then need to work out the value of this function at t naught plus dt, and you know what the value of f at t naught is, then you do all of this, and you work out the value of f at dt. Okay. Now I'll take a pause here, people. I'll take a pause here, and the floor is open for discussion. I've given you one condition for when Taylor's theorem is true. Can someone tell me what other condition is required for Taylor's condition to be true? It's all written on this slide. Can we take 5 minutes with comments? No comment or response is right or wrong. It's just a comment or a response. Anyone, please? Can you comment? What's the other discussion I need? Or what's the other condition I need? People? Keith, help us. Get it started.
Sorry, sir, what was the question?
The question is, dt has to be small for this Taylor's expansion to be true. What other condition can you think of for this expansion to hold true? Look at that red line. Look at that massive number of d's that I've written on the slide. What can you say from there? Yusuf? Clara?
Is it continuous?
That's right. And how often continuous does it have to be, Clara?
Infinitely, or
as much as need be.
okay.
Exactly. Thank you, Clara. I really appreciate that. And so all of these derivatives must exist. I mean, once we know it with hindsight, it's very straightforward to appreciate it. But Clara's pointed out something really important. All these derivatives must exist for a Taylor series expansion of any function to work in our favor. Okay. And so if this red line is broken or something, this Taylor series expansion will not work. Okay. Now fine. So this was for any old function. And this is for a very specific function, Keith, where your x is a small number. I've forgotten to put the absolute value signs over here, but x is a small number, okay? And so 1 over 1 plus x, according to Mr. Taylor or Mrs. Taylor, or whoever it was, 1 over 1 plus x expands to 1 minus x plus x squared minus x cubed, so on. It goes on infinitely. Okay, and this is relevant. So the condition here is not epsilon, it is x, but x has to be small. Small as in compared to what? Well, compared to what must x be small? X has to be numerically much smaller than 1. You could replace the 1 in the denominator here by some a, and then the condition might change to x being much smaller than that a. Okay, so not writing an a here doesn't really make much of a difference, right? So this is an expansion that we might be using in a minute. If on the left hand side you have 1 over 1 plus x, then a series expansion is 1 minus x plus x squared. As soon as we remember 1 minus x plus x squared, that is more than plenty for our purpose, for today's purpose, for a couple of years purpose. Okay. So those were Taylor's expansions, and now I will move on to discussing a few methods for ordinary differential equations, followed by a few methods for partial differential equations. And so, if my ordinary differential equation is written in the form on the top left-hand corner, say I have a state variable x with an independent variable t. The total derivative is dx by dt with some given function. So Randa stuck with cardiomyocytes, exactly like this. I'm stuck with smooth muscle cells, exactly like this, and so on and so forth. Then the simplest way to go about solving this equation is by using something called an explicit Euler method, where the new value of x at time t plus dt, the new value of x at time t plus dt, is simply the sum of the known value of x at time t. So you know the value of time at time t, and to that you add dt multiplied by whatever the function f works out to at time t. Okay, so all you have to do is plug in time t and the value of x at time t, take this value multiplied by dt and add it to the previous value of x, and that's what gives you your new value. Okay, now this is explicit Euler's method. Extremely straightforward to implement. Yeah, 2 or 3 lines of code and you're there. Now, as an example, we can take a very simple first order differential equation here. Lambda is a constant. Yeah, you might also call lambda the stiffness of the system. And we learned back in January that if you have such a differential equation, you take a pen and pencil and paper and you immediately write down the exact solution. You do not need any computer there. Okay, you do not need any computer. But you can also generate your solution by induction, as shown in the bottom left-hand corner. Okay, and as you can see, as your n increases, as your time keeps increasing, unless lambda is of a certain nature, I wonder what nature that has to be. But unless lambda is of a certain nature, this term here is just going to keep expanding too much, regardless of how much your dt might be. Okay, and so I wish that we apply ourselves and answer the question. Apply ourselves, put this together, and answer the question. Is a stable solution, that is yn, existing for all n's, n 1, 2, 3, 4 million, zillion, trillion, is a stable solution guaranteed when dt is small? Can anyone unmute themselves and either say yes or say no? If you use an explicit Euler method, is a stable solution always guaranteed if you were free to take however small a dt you could? Can someone please unmute themselves and give us a yes or say no? Anyone, please? Gabrielle? Lawrence? I cannot hear you. That's fine. So just to sort of, that was a question that leads into the next slide here, and it's our misfortune. We are unfortunate that even if you chose a very small dt, the explicit Euler method may not always work. It often works. It often works, and that is very useful, but it's not always guaranteed to work. And why not comes up in a couple of slides. But before that, let's talk about another very widely used method to solve ordinary differential equations of a very special kind, in that if you had a differential equation, okay, if you had a differential equation such that dy by dt had some function of y in the numerator, and some function of the state variable in the denominator. Then two fellas, one called Rush and another one called Larson, have told you that your solution at time t plus dt, your solution at time t plus dt is simply the sum of the y infinity function over here, which totally doesn't depend on time at all. It doesn't depend on time. And to that you add yt, which is known. You know the solution y at time t minus y infinity multiplied by some exponential term here. Now, given Russian-Larson's method, this works especially well for describing ion channel gating mechanisms. This differential equation up here describes exactly an ion channel's gating mechanism. And Russian-Larson tell you that the solution is something half as elegant as this, something as elegant as this. And so there may be additional terms here. Typically, we are thinking about the error here. Okay, so I wonder what the error over here is. But we may be excused to thinking that the error in this method is virtually zero, because we have a almost analytical solution to go from one time step to the next time step. Mind you, people, even as we have made a analytical integration here, your solution gets better as your dt is smaller. The difference between Russian-Larson method and the explicit Euler method is that the Russian-Larson method is likely to succeed for a large range of choice of dt, but the Euler method is somewhat more restricted. Okay, and so this was method number 2 for ordinary differential equations, the Russian-Larson method, people, Russian-Larson. Coming back to the explicit Euler method, as we discussed, Euler method can be programmed very easily within 2 or 3 lines of Python code. We are done with the explicit Euler method. But here's me sort of showing you an example of one example of when it may not work, as well as slightly exploring why the explicit Euler method did not work in this specific case. And so the differential equation that we have as an example is written in the top left-hand corner. Y prime is minus 21y plus e raised to minus t. Yeah, and your initial condition is pretty simple. You know, y naught is 0. So you are given the initial condition, and you're asked to work out the numerical solution. Now, even before we pull off a numerical solution, let's see what the exact solution looks like. It looks like this, as shown in panel A. That's the exact solution. You can do a little bit of 5 or 6 line pen and paper calculation, come up with this exact solution. But fine. Next thing you do is shown in panel B. Pick a dt. It doesn't have to be 0.1. You can pick a small dt. You can pick a large dt. You pick your dt. Okay. And in comparison to still the exact solution shown in red, the diamonds here, the squares here, rotated squares here, show you the numerical outcome of an explicit Euler solution. In this case, taken at dt is equal to 0.1. Okay, and you can see that the numerical solution is nowhere close to the exact solution, which is a little bit of a bummer. And one of the reasons why the numerical solution does not come anywhere close to the exact solution is because of the stiffness of the differential equation. The stiffness is the minus 21 over here. Okay, and never mind that it is nowhere close to the exact solution. As the solution progresses, it indicates that it is also divergent. So the solution is not convergent. Okay. So the solution is not convergent. And the reason why this solution, this differential equation, or rather this numerical solution does not work, as I said, is because it is stiff. And graphically, you can see that the phase portrait or some graph has very high slopes close to your solution. And that is the reason why the numerical method of explicit Euler method in this case fails spectacularly. So be wary. Use Euler method as a first recourse because that can be programmed within 10-15 minutes, but be wary. But fine. So and so then the question then becomes, if I then want stability, what then must I do to make my solution stable? And the first thing comes to my mind is to make your numerical method implicit. Okay. So what do I mean by making your numerical method implicit? In that, if you have a differential equation of this kind, dx by dt is f of x, then the value of x at the next time t plus dt, the value of x at the next time t plus dt is worked out by taking the value of x at time t, so you know the value of x at time t, and to that you add dt multiplied by the function f worked out at time t plus dt. Okay, and so since f is worked out at time t plus dt, the x also has to be at time t plus dt, and therefore you can appreciate that on both sides of my equal to sign I have xt plus dt. Xt plus dt is my unknown, x at t is my known. Okay, and that is what makes it implicit. As soon as you know how to discretize your differential equation in an implicit manner, incidentally, this written like this, the bottom row of the left-hand side set of equations, that's the first term of your backward difference formulae solver that Tim and Jeremiah use, that Clara uses. That's the first of the sixth order solver. And so that's how it looks like. And as soon as we know how to do the discretization, you have then written it in implicit form. And this implicit form has indefinite stability. There's no condition. Accuracy is not guaranteed at all, but stability is definitely guaranteed in an implicit formulation. So your implicit formulation at first order people. This is your first order implicit formulation. Okay. And you might appreciate that this thing already starts looking like a term from a Taylor series somewhere. Okay. In case someone is interested, this is second order accurate, because you've taken all terms till up to the first power of dt, but you've chosen to ignore all terms that are multiplied by dt squared and over. So dt squared multiplied by something is ignored. dt raised to 3 multiplied by something is ignored, and so on and so forth. Second order accurate. Yep. And so as a piece of information, you might wonder, you have xt plus dt on one side of the equal to sign. You have xt plus dt on the other side of the equal to sign. However, will you solve for xt plus dt, given that you know f and x at t? And the solution was provided by one Isaac Newton, and you go through several iterations, okay? And you then converge to your solution xt plus dt. Okay. It's somewhat related to Newton's that we discussed several slides ago. But fine. Moving on to the actual method that is provided in the solver, okay, in the PM3 solver. And this is the backward difference formulae based method. And this method, thankfully, did not require our programming. We had to prudently choose functions from a Euler library provided by Alan Hyde-Marsh from Los Alamos National Laboratory. In that, if you have a set of differential equations, say dy by dt is f of x and t, I apologize, this x should read y. And y in general is a vector. It doesn't just have to be one y. It can be y1, y2, y3, y4. Y can be a vector. And if y is a vector, then this f is also a vector. And there's vectors all over the place there. So this can be vectors. But given a set of differential equations, dy by dt is f of y, comma t, then backward difference formulae essentially means work out these coefficients alpha ni and beta ni such that this combination of the solution or the initial conditions and the derivative combine to become 0. Okay, and then can you let J in? So the sixth order backward difference formulation, the solver that we have right now that we are using all over the place in several projects, is based on this sixth order formulation. We use the sundials library for this. And this is a stable, as accurate as it gets solution. And this is the solution provided to you by the PM3 OD solver. Your part is to systematically work out this right-hand side F here. So there's no magic here. As soon as you give me this right-hand side F written in a suitable form, very straightforward form, very intuitive form, the most robust solution is at your fingertips. I might take a minor digression here and say that one immediate next step is that our systems are now not only differential equations, but they are also differential algebraic equations. Algebraic part being, for example, say TIM's a lot many feedback mechanisms. So these are state variables, but they do not have a differential part to it. They're just algebraic equations. Yeah, fine. They describe some sort of conservation that is necessary to describe the system. Yeah, fine. And so a certain level of modification is required. Not much, but a certain level of modification is required before we sort of progress our current edition of the solver to the differential algebraic equation solver. Yeah. Okay, fine. So that was ordinary differential equations here. And so I would promptly now move on to discussing something about partial differential equations. And for the sake of simplicity, I will stick to a manageable partial differential equation that has a transient part on the left-hand side of the equal to sign. There's a time derivative. And on the right-hand side of the equal to sign, we have the second derivative of a variable. The upside down triangle means that it is taking a gradient. And if you apply the upside down triangle twice, it is read as del squared. And del squared means you are asking what is the diffusion of the variable v if I apply gradient twice. So upside down triangle means gradient, and if you apply gradient twice, it means diffusion. So right-hand side of the equal to sign is saying, here's the diffusion of any which state variable v that you might have. And so this is the simplest PDE that I thought I will use to explain a couple of numerical methods to you. And so the first numerical method, again, similar to ordinary differential equations, is the simple Euler method. And so given a differential equation, never mind the 3D form of the simple differential equation, if I just have the 1D description of the differential equation as shown on the left-hand side of this slide, then the discretization of this one-dimensional differential equation, partial differential equation, partial because you have two independent variables here, t and x. And only in this case, superscripts track time and subscripts track space. The discretization might look something as horrible as this. And if we walk through this, what it means is that the value of your state variable v at time t plus 1 at any location I in space on your mesh, yeah, is the sum of your state variable at time t at the same location multiplied by this horrible central differencing term here. Okay, the dx here is what Randa calls the resolution, mesh resolution. Mia Wang also calls it mesh resolution. Okay, written in this way, this is your explicit Euler method description of a simple partial differential equation. And there are some rather restrictive conditions on the dt, assuming that your dx is driven or dictated by your image resolution, perhaps. And that restrictive condition in 1D is called the Courant-Friedrich-Levy condition, the CFL condition, the Courant-Friedrich-Levy condition for stability. And what it says is that dt cannot be anything more than the ratio of dx squared divided by 2d. Okay, and so if your dx is 0.1 and your d is say 2, then your dt is already a very small fraction of 1. It's already a very small fraction of 1. And that is the Courant-Friedrich-Levy condition. As you go from 1D to 3D, this condition is further restrictive. CFL condition is a necessary condition. It must be satisfied. If this condition is not satisfied, your numerical scheme is guaranteed to fail. If this condition is satisfied, your numerical scheme may succeed. It is not guaranteed to succeed. Necessary condition. Okay. So that was your explicit Euler finite difference scheme for a very simple PDE. Again, this is very straightforward to program, and therefore this should be this must always be our first port of call. Okay. However, if you then ask for, if you then say I want to improve stability of my Euler method, say for example for reasons that you want to increase your time step so that you can do lots and lots of simulations, then an implicit finite differencing comes to the rescue. It comes to the rescue, and that finite differencing is illustrated on the top row over here. So again, I stick to my one-dimensional partial differential equation here. And you can see that I'm trying to work out the value of v at the space location I at t equal to 1 using the previous value of v at that location. But I'm also using the values of v at the next time step at the nearby locations as well. Okay, so there are at least 4 values in the future that I'm trying to use here to work out values in the future. And when your values in the future appear on both sides of the equal to sign, that is a strong indication that your finite difference scheme might be implicit. By writing your finite differencing scheme to be implicit, you are gaining a lot of stability, and it is unconditionally stable. There's no guarantee of accuracy, but it's unconditionally stable. That you have. Okay, not much use, but for what it's worth, it's there. life, although, then gets worse in that if you've written your finite difference scheme as implicit as this, then you really cannot solve for your state variable v for each location. You must solve for all v's at all locations in your 1D, 2D, or 3D model at the same time. Written in matrix representation, it looks as drawn on the bottom right-hand side, where you have on the left-hand side of the equal to sign, you have the known values of your state variable now. Yeah. So this J represents time now. Yeah. I've written the timestamp as a subscript. This picture has written the timestamp as something after the comma. And so on the left-hand side, you've got the known values u, all in a row. You've got the unknown values of u, all in a row on the right-hand side of the equal to sign. And this matrix here comes out of working out multipliers to all these terms here. Yeah. Now, two things to remember here. I wish others were present, but two things to remember here, people. Firstly, these equations turn out as something known is equal to something known multiplied by something unknown. So how to get this something unknown from these two something knowns is a question. So obviously you have to invert this matrix here. But the more important thing to realize here is that you can see that there's a whole bunch of zeros that you have. Okay. And these are called diagonal matrices. These are also called sparse matrices. A whole bunch of people in our town and university spend a lot of time solving and manipulating such sparse matrices to make efficient solutions exactly as shown over here. Okay, so this is a sparse matrix. Sparse matrices come up very, very often in our lives, and we have to know how to deal with sparse matrices. One starting point would be an excellent library called Trilinnios. Do a little bit of maths, find out how Trilinnios does that maths, and you are done. Okay. So this is unconditionally stable. You have sparse matrices. To get your unknown vector, you have to invert this matrix. And inversion of this matrix, to invert this matrix efficiently, you use its sparsity. You exploit its sparsity. And after inverting this matrix, you then multiply the inverse to this thing that you know. And by doing that multiplication, you then find this solution at the next time step. First order implicit method, people. First order implicit method is still Euler method. And so this is how I run the first order implicit method. Now, as it turns out, the implicit method is okay, it's stable, it's really nice, but it's not accurate enough for the purposes of, say, for example, running electrical waves through the mouse hearts that Randa needs to run her electrical waves through. And so the prescription to improve your accuracy is to go a higher order. So far, so without justification, I might sort of remind ourselves that this is first order, stable, but not much use because it is not very accurate. And so the prescription then is go higher order. And a practical problem presents in that all tissues, human atrial tissues, never mind mouse atrial tissues, vascular wall tissues, are pretty thin. And if you put those tissues on a grid like this, either on the blue grid, which is at time now, or on the white grid, which is at time next, barely 2 or 3 grid points describe this tissue or the shape of this tissue. And so your higher order schemes need to be elegant. and another word for elegance is called compact. And so the current generation of finite difference solvers, especially in VCPL, are fourth order compact finite difference schemes. And roughly about what they do is that if you're looking for the solution at this blue point at the next time level, so you want to go from this blue point at the middle to this white point at the middle, go from now time to the next time, you are allowed or you have access to its neighbors, okay, to its nearest neighbors in a finite difference grid. You do not have access to, say, for example, I-1 or I+2, okay? And that's what the compact means. Now, the bottom right-hand side image shows you something that people in our Rotman Institute have been working on. And this is a very visually attractive representation of a linear algebra method developed by Robert Corliss called Bohemian Matrices. He calls them Bohemian Matrices. And this image is some unthinkably beautiful representation of the workings of Bohemian matrices. And so Rob Corliss is in the Rotman Institute of Physiology on campus. So there you have, and the purpose of showing this Bohemian matrix is that Bohemian matrices are the ones used to efficiently solve your sparse matrices. Okay, so this is what Rob Corliss may or may not be doing in the last few years. Now, fine. So we are using fourth order compact schemes. We will come to a couple of details of it, not much. But before that, here's a couple of pictures. You know, I like these two pictures. And rather elegant pictures. On the left-hand side is a piece of art situated just outside of Milan's central station, train station. And that's a mending heart. Because Milan's train station is also on the way to the northern Italy's largest hospital. So you get out of the train, you walk past this thing, and you go to a very large hospital campus. And this apparently is a heart that has been patched up by the local clinicians and whatnots. In Milan is also a whole bunch of computational scientists who are interested in the heart and the brain and blood flow and everything. As soon as you get sick of treating your critically ill patients, you may wish to waltz on to what's shown on the right-hand side. It's called A New Point of View. It's run by an exceedingly accomplished chef. And she actually comes and talks to you. And is situated somewhere in the Alps. And she gets to know you before she feeds you. So the Citamani in Milan, people on the right-hand side. The Citamani, also A New Point of View by an accomplished chef. So coming back to fourth order compact differences, and you might ask, what is this fourth order compact difference scheme? And so promptly, let's then sort of change our minds and consider a partial differential equation where the state variable u is double differentiated with respect to the x variable. And maybe there's a couple of more terms like that. I will stick to the first term. So this is d2u by dx squared. The subscript means d2u by dx squared. And the first thing that you do is define a central differencing operator. People, please do sort of take this. I need a little bit of help from you, okay? So you define a central differencing operator. Call it the Greek symbol delta. So this is delta, you know, you could just write D over there, you know, but this is delta. Define the central differencing operator delta. Yep, and delta squared then So delta gets defined, this operator. Operator means it does something to a variable. In our case, it's VU. Okay. And so the operator delta, the central differencing operator delta, gets defined as a square. That is, you take the value of u at the location I plus 1. So in the x direction, you look for your neighbor in the +1 direction. To that, you add the value of u in the x direction, one behind you, the neighbor behind you. And from this addition, you subtract twice the value of the variable at ijk. And that is the definition of the differencing operator. I forgot to write u over here. I forgot to write u over here. That's the definition of the differencing operator. Yeah. And after manipulating the differencing operator with the PDE, we get to the place where the second derivative of the variable is defined as a ratio of operators. You have a ratio of operators where you have delta x squared. But fine, you know what to do with delta squared if it was on its own. Yeah, okay. But life gets worse. It is then divided by an operator of 1 plus 8/12 of delta x squared. And that is the term that gives you the fourth order terms. Yeah. And because you are lucky enough that your PDE is admirable, there are no convection terms here. There are no first order derivatives here. You can then quickly get to the fourth order derivatives, either by using the differencing operator or by manipulating your PDE here. All of this is valid inside the domain, not at the boundary, not on the outside, not at the boundary of where your blood vessel is in touch with blood, not there. Not where your blood vessel is in touch with the outside, not there, but inside the domain, wherever you're solving either your CFD Navier-Stokes or your elasticity equations inside the domain. So this is thankfully implemented for at least inside the domain. No, it is compact in that, as written in the top message in the yellow box on the right-hand side, you only need nearest neighbors. You do not need I plus 2 or j minus 3 or something like that. You don't need to, okay? And that's what makes it compact, and that's as good as it gets when you're dealing with really thin tissues, okay? So the use of compactedness is useful in a few different ways. Now, as I said, this fourth order method is already described and implemented in the solvers accessible to you, but the space for development is that the boundary conditions are still first order. Unfortunately, they may still be explicit, and therefore the overall scheme is not fourth order implicit super accurate. Your chain is just as strong as the weakest link, and the weakest link here are the explicit boundary conditions. So I wish I'm looking for help on that. Okay. We have some starting material. I have some notes, yeah, and we can start from there. Comes a little bit of policy in that this is how the geometry files in PM3 format are written. So this, I believe, is specifically mine and Randa's problem, which we have resolved. But we have a policy on how geometries are written for our structured finite differences. Another sort of thing I would like to bring your attention to is that if your physics has several terms on the right-hand side, as shown here, where you have diffusion shown in purple and reaction shown in red, you might wish to adopt something called operator splitting. Yeah, and you solve the diffusion part using your implicit methods that we have discussed in the past several slides. And you then solve for your reaction part at that location. And if need be, you go through several iterations of solving, firstly for your spatial part and then for your other terms part. And that way you inch from your existing solution to your desired solution at the next time step. Shown here on the right hand side is a behavior of the iterative sort of manner in which SimVascular performs its sparse 1D solution. You can see that it proceeds through iterations on the left hand side. There is an acronym called NORM-F. I believe that is the norm of some description. You can see that the norm starts quite large, but eventually reduces to a small value. And I believe this is the tolerance set by Lawrence for that, for his solution. And then there's other details there, okay? So the first time step could be solved in a total of 3 iterations for this specific model. Which model this is, I don't know, but is an example of iterative solvers behavior, okay? Even implicit. And so here's a reminder to myself and to my young friends, Tim and Jeremiah, in that just because your simulation doesn't produce any errors doesn't mean you are on the home run, you know, far from it. Just because you have a little bit of stability, it does not mean your solutions are meaningful at all. So we have to be careful of many, many things. It is our responsibility to be careful. And with that, I believe I finished discussing about finite differences and how you could do explicit and implicit finite differences sort of for now. We can talk about that much more after. In terms of finite elements, I present my apologies, and I will not show you the workings of finite element analysis because that is an exceedingly long discussion. It has to be broken down into several pieces. So all being well, we will make videos or presentations about finite element methods and how to implement finite element methods in the upcoming months, definitely before the next academic year is finished. Okay, but approximately you have something called weak and strong formulations. By definition, finite elements are always implicit. I believe the finite element solvers available to us are first order. Okay, I could be wrong, and I strongly suggest that you start with the book showed on the left hand side, Schaum series. Very elegant, very nicely done. It has bucket loads of problems. Yep. And if you're looking to use finite elements through a commercial solver, then Saeed Movani walks you through on how to use finite elements for your specific problems using ANSYS. ANSYS for all Western University people is available to you thrice over through specific certain channels. ANSYS is widely used. And if I dig deep enough, I might be able to come up with some ANSYS scripts that will get you started. So I use these 2 books, and so I thought these are a couple of nice textbooks that get us started. Okay, and approximately the maths of finite elements is the same as the maths for implicit finite differences, in that you do some magic trickery to a partial differential equation and you come up with a set of linear equations, and you are then faced with a linear algebra problem rather than a differential equations problem. And good luck to you who's solving for you, given that you know K and F. That's where you spend most of your time if you are a programmer for finite elements. Okay. So as I said, it's a whole bunch of linear algebra. There are exceedingly efficient ways of doing something. Yours truly is already doing it in Trillenius and Petsky, but there's a whole bunch of other libraries that will give you these solutions. You have to make use of the sparsity of these matrices. You also should use preconditionals. There is something called preconditioning, and it will come your way. I refuse to go into what preconditioning is at this moment. Okay. Everything that I have just described, everything that you guys are using is something that I would classify as brute force. Finite difference and finite element methods are brute force. We discretize our system and then we somehow crunch out numbers. But there are much more elegant methods out there, and they have to come our way at some early date. And to mention a few, the first elegant method that I would like uptaken by us are spectral methods. Very, very elegant. There's other methods, mesh-free methods even. Yeah? And so Barcelona HPC have done it. Alejandro Frangi and company have done it. Frank Sachs and Gunnar Zeman have also done it in Freiburg. There are finite element methods that are exceedingly efficient without any compromise on accuracy, especially if you want to do inverse problems. One of the things that we have to do is to exploit model-specific properties. And as Dr. Goldman said, if we have sources, if we have multiple sources, then people have already given us solutions for exploiting such a property. And let's say that property has a name, Green's function, and it will reduce a whole bunch of hassle for us. So we have to exploit model-specific properties to make our lives more organized. And so these are the other methods that are on the horizon. Okay. To mention specifically, I would like for us to look into platforms. One is called Nectar, exceedingly elegant blood flow simulations using spectral HP methods. And the other platform, a very advanced platform from University College London called HEMI LB. It uses a yet different Monte Carlo method called a lattice-Boltzmann method. And both of these things are free. So this is definitely up for uptaking by us. The file input or output concerns, I will not go into now. Here's Mr. Bean. I met him at the fountain at Piccadilly in the circus. So that is the brown Mr. Bean. He's definitely better looking than me though. And so I believe this is where I will stop. Thank you all for your exceeding patience. Yeah? And I will stop here. Open to questions. Not that I have all your answers, but open to questions. Yes, Keith.
There is just two related questions I have, Dr. Kharche. One of them is, you mentioned on the last one that a Green's function method is something which is a possibility if you know your sources of O2. So are there methods that exist in PM3 that you have to like integrate kernels numerically? It's
not within PM3, but I believe between Dr. Goldman and myself, we have a copy of Timothy Seccombe's code somewhere.
Oh, I see. Okay.
Exactly what you're saying. And Timothy Seccombe lets you download his code. It's as easy as that.
Awesome. And the other question I had is, if you have, let's say, like, you know, the cases we saw so far are PDEs, especially because it triggered my memory. You were mentioning the other day about porous flow. As something that was capturing your attention. And I know that they're innovating fractional PDEs for that purpose. And is that something that can be expanded into some of the solvers?
Definitely. So fractional derivatives is definitely something that we have to be doing. And I believe generating numerical schemes for fractional derivatives, Keith, is exactly as written over here on slide number 51. So it's not as simple as written here. a fractional derivative is much more hard work, much more hard work, but is definitely, we have to do it. Now, regardless of whether it's doable or not, we have to do it because there's a lot of physics in there. Yeah.
Interesting. Cool. Thanks. Thank you. I've been hearing a lot about it, especially for porous flow, which is why it was triggered in my head. And so I've only heard of Galerkin methods. I haven't heard of anything else applied for fractional problems. So yeah, it's an interesting problem. Thank you.
So for everyone else's benefit, Keith has just mentioned yet another method called the Galerkin method. Okay. So those who may end up programming for a living have to pay attention to that. Clara, do you have any comments on that?
I think it was interesting going into more detail about the PDs and ODs, and I noticed that some of the at the start you talked about some concepts that I think were covered sort of in the first year applied math course. I don't really put it into practice as much, so it was good to review them. I think it was specifically the I think the vector fields. It reminded me of the slope diagrams that we were analyzing. So it's seeing that it has applications in the works that we're doing it reminds me how important those kind of fundamental maths are.
Riva, tell me, what do you think? Tell me.
I thought it was a very interesting presentation. A lot of new concepts.
You're just saying.
No, actually, I don't really have a very strong math background, and a lot of these equations were new to me. So it was really interesting to see how a lot of, I guess because I come from a physiology background, I don't really see how so many equations are related. So it was nice to see the connection between, I guess, the math perspective and then the human body, because I'm sure this is all applied to that.
Okay. So is Randa here? No. Jay, what did you think? Do you have any comments for us? Jay? Dr. Goldman, would you have any advice for us, please?
Here I am. Advice. I don't know.
Any comments?
Yeah, I mean, I think it's good to understand, I mean, in SimVascular and all that, we provide all these codes that do all these things, but to have some understanding of what's really going on, I think helps a lot, especially the students, which I think is most of our students who aren't, math people, that's not their background.
No, there's not.
I think it helps a lot. And also to take some of the mystery out of it, that these things are not, it's not magic, and almost anyone can do it if they just work on it. So I think that's important. Yeah. And when things don't work, there's usually a logical explanation that we can figure out. It's not just, call your supervisor and tell them they need to fix it, because the magic isn't working.
That's
so
right.
there's usually something in there that
That's right.
you can figure out.
Yes. Yes. Thanks. So I propose that Daniel stop recording, but we will keep this Zoom